Okay, so this is the second part of the iGCSE Introduction to Radioactivity. It focuses more on sort of properties and half-life and things like that. So we've got, first of all, penetration power. So different radiation will penetrate differently due to their nature. Um, so some are particles or waves, and it depends as well maybe how much mass they have and how much charge they have to how much they ionize. So you have alpha, that will generally be stopped by air or some paper because it's quite highly ionizing, so it ionizes the atmosphere. Beta, smaller particle, fast moving, penetrates through the paper, but generally stopped by a few millimeters of aluminium because it's also quite ionizing. Gamma passes through both the paper and the aluminium because it's a wave. It's very penetrating and it needs a lot of centimeters of lead or many meters of concrete to absorb most of it. But they can still pass through even really thick concrete because it's got no mass, no charge because it's a wave. You should know about this properties table really, which is you've got your symbols, so alpha, beta, gamma. You've got the masses, you've got the charges, and you've got charge to mass ratio. So I've just taken the charges, so +2 divided by 4 relative masses gives me +0.5. The beta particle is -1 charge divided by 1 over 1840th, or it could be 1 over 2000, which gives me a charge to mass ratio of -1840, which is huge, which means it's affected a lot by magnetic or electric fields, i.e. strongly curved. This one curves, but this one's zero. Zero charge, zero mass. Paper or skin is stopped by, for alpha, so 10 centimeters to 1 meters of air. Aluminium, we said, or 10 meters of air. And gamma, thick lead, or 30 centimeters of concrete. And the ionizing power, as you can see, are a lot. A sort of a medium, and then not very much at all. So we definitely don't want to use alpha inside the body because of the ionizing problems, but beta we do and gamma we do because it's not as ionizing. But alpha outside the body is particularly safe. Just don't get it anywhere near your nose or eyes. Nuclear equations, we should be able to write out the 3 nuclear equations, but remember, we could have any atoms here at all. So what they tend to do is they want you to know one of the missing numbers or 2 of them. So we're talking about all of the numbers at the top should add up, all the numbers at the bottom. And you should be able to identify alpha, beta, gamma for each equation. And then radioactive waste. So ionizing radiation, that causes problems which arise in the disposal of the waste, which has lots of risks, needs to be managed. You should have an idea about what to do for maybe like a 6-month question with different things with different amounts of radiation. Half-life time, we can't predict when the nucleus of one particular atom will decay. It's a random process. However, we can plot a graph to show the time it takes for half the sample to decay is a fixed time for each isotope. And in this case, it's every 2 days. So we start off with 80 counts. So that's not the number of atoms. This is just activity. So 80 atoms or nuclei are decaying. And so after 2 days, it's given out 40 particles. But then after another 2 days, it's only given out 20. And so we get this really cool graph and we can pick a half-life. You should be able to do 3 little checks like that to work out a consistent half-life time. So there you go. That's half-life. And that's the last bit of 7B.